Hey everyone, and welcome. Today we are cracking open the ultimate rulebook for how literally everything moves. We're talking about Sir Isaac Newton's 3 legendary laws of motion.
But let's start with a question you've definitely experienced. You're on a bus, it slams on the brakes, and your whole body lurches forward, right? Why does that happen? Well, it isn't some weird magic trick. It's pure physics. And by the end of this, you'll know exactly what's going on.
And that experience brings us straight to Newton's first law. I like to call it the law of stubbornness, because it's all about a simple, powerful idea called inertia.
So what even is inertia? It's basically the built-in resistance that every object has to changing what it's doing. If something's sitting still, it kind of wants to keep sitting still. If it's rolling, it wants to keep rolling. That's stubbornness, that resistance to change. That's inertia. And the more mass something has, the more stubborn it is, the more inertia it has.
And once you know what to look for, you see this stuff everywhere. You know that classic magic trick where someone yanks the tablecloth out from under a full set of dishes? That's inertia. The dishes are just being stubborn. They want to stay put. Or when you're trying to get ketchup out of a bottle. You swing the bottle down and stop it suddenly, but the ketchup's inertia makes it want to keep on moving, hopefully right onto your fries.
Okay, now this slide tackles a huge misconception that a lot of people have. We tend to think you need to keep pushing something to keep it moving. But Newton's first law tells us the exact opposite. An object in motion will stay in motion all by itself. Thank you very much. You only need a force to change that motion, to speed it up, to slow it down, or to make it turn. And that change, that's what we call acceleration. So, if the first law is all about an object's desire to just keep doing its thing, the second law is the one that tells us exactly what it takes to change it. This is really the mathematical heart of Newton's rules.
And to really get it, we first have to talk about something called momentum. Just think of it as mass in motion. An object's momentum is just its mass times its velocity. So the heavier it is and the faster it's moving, the more momentum it's got.
Yeah, a really great way to feel this concept is to think about how much oomph or impact it has. A massive truck moving really slowly has a ton of momentum. But guess what? So does a tiny little bullet that's moving incredibly fast. They can both deliver a huge impact, and it's all because of their momentum.
So let's use this to solve a little puzzle. When a cricket player or a baseball catcher catches a super fast ball, they always pull their hands back with the catch. They don't just hold them still and let the ball smack into them. Why do they do that? Well, it's not just for style, it's pure physics.
And the answer is hidden inside the true definition of Newton's second law. It says that the force you feel is equal to how quickly the momentum changes. You see, to stop the ball, you have to get its momentum to zero. You can do that with a huge force over a very short time, or you can do it with a smaller force over a longer time. The secret ingredient here is time.
And boom, here's the solution. By pulling their hands back, the fielder is cleverly increasing the amount of time it takes for the ball's momentum to disappear. And when you increase the time, you dramatically decrease the force your hands feel. If they just held their hands still, the time would be almost instant, the force would be massive, and they'd probably have a broken finger. Ouch.
All right, let's get to the third law. This is the one you've probably heard a million times, but it tells us something really deep. Forces never ever show up alone. They always come in pairs. For every action, there is an equal and opposite reaction. Simple enough, right? But here is the critical detail that almost everyone misses. The action force and the reaction force are always acting on two different objects. When you push on a wall, that's the action. The wall pushing back on you is the reaction. The forces don't cancel each other out because they're not acting on the same thing.
And this is happening constantly. A rocket pushes hot gas down. That's the action. And the gas pushes the rocket up. That's the reaction. When you walk, you're actually pushing the entire planet Earth backward with your foot, and the Earth is pushing you forward. It's this beautiful, constant dance of forces.
Okay, here we go. This is the big payoff. Because when you take all 3 of these laws, the stubbornness of inertia, the force-momentum equation, and the action-reaction pairs, and you put them all together, you get one of the most powerful and fundamental principles in all of physics. It is the law of conservation of momentum. And it basically says this: in a closed system, the total amount of momentum before something happens has to be the exact same as the total amount of momentum after it happens. Momentum can't be created or destroyed. It can only be passed from one object to another.
Let's see this in action because it's so cool. Imagine an astronaut floating in space, perfectly still. The total momentum of the astronaut and ball system is 0. Now, she throws the ball forward. The ball now has momentum in that direction. Well, to keep the total momentum of the whole system at 0, the universe demands that the astronaut gets an equal and opposite amount of momentum, pushing her backward. And since she has way more mass than the ball, she'll drift backward much more slowly. But the momentum exchange is absolutely perfect.
So these 3 laws are just unbelievably powerful. They describe our world, the world we see and touch, with almost perfect accuracy. But they aren't the final word on the matter. They actually do have their limits.
I love this quote here. It says that Newtonian mechanics is a limiting case of broader frameworks. Basically, Newton's laws are an absolutely essential, foundational piece of a much, much bigger puzzle.
So where do these rules bend? Well, they start to break down at the absolute extremes. When things start moving close to the speed of light, Albert Einstein's theory of relativity takes over. And when you zoom all the way down into the strange world of atoms and particles, a whole new set of rules called quantum mechanics is in charge.
What's amazing is that Newton gave us the rule book for the entire world we experience every day. But his work also paved the way for us to eventually discover that there are other, even stranger rule books for these other realms that we can barely imagine. And that just makes you wonder, what other rules are still out there, waiting to be discovered?